These two sentences contain the same 5 words. The dog bit the man. The man bit the dog. Only 2 nouns traded places. But the attacker became the victim, and the victim became the attacker. If a language model knew which words were present, but not where they appeared, it would miss the difference that matters most. That creates a strange problem for a transformer. Attention is excellent at comparing tokens. On its own, though, content-only attention has no independent coordinate system. Nothing inside the word vector for dog says, "I came before bit," or "I am 3 places away from man." So word order has to enter the computation somewhere. It can arrive as an address attached to each token. It can appear as the distance between 2 tokens, or it can become an angle hidden inside attention itself. That last version is the clever one. To see why, we first need to remove position completely. Give attention 5 content vectors, 1 for each toy token in the sentence. The layer turns them into queries, keys, and values, compares them, and produces 5 updated outputs. Now, shuffle the 5 input rows. If there is no positional signal, the computation shuffles with them. The same token content creates the same pattern of comparisons, only rearranged. Attention can still notice that dog and bite-related content are relevant to each other. What it cannot recover is an external fact such as dog was first, man was 5th, or this noun came before the verb. This property is useful. It lets attention process all positions in parallel without assuming that the input must be read 1 step at a time. But parallelism removes the natural clock that a recurrent network gets from processing token 1, then token 2, then token 3. Decoder-only language models do have one extra clue. The causal mask blocks attention to future positions. That creates a before and after boundary. It still does not replace the richer position signals used by standard transformers, and causal masking gets its own episode next. For now, our content vectors need coordinates. The simplest idea is to give every slot an address. Position 0 receives 1 vector. Position 1 receives another. Position 2 gets a third, and so on. Add that position vector to the token vector, and the model no longer sees dog alone. It sees dog at 0. Move dog to position 4, and the content stays dog, but the combined representation changes. The original transformer generated these address vectors with sine and cosine waves at many frequencies. One pair of dimensions changes quickly from position to position. Another changes slowly. Stack enough of those waves together, and every index within the working range gets a distinctive multi-scale signature. The position vectors can also be learned. BERT, for example, sums token, segment, and position embeddings. In that design, the model learns a table of position signatures instead of calculating them from a fixed formula. Absolute addresses solve our first problem. The 2 dog and man sentences now produce different combined vectors because dog and man land on different slots. But an address is not always the relationship we care about. Suppose an entire phrase slides 20 positions to the right inside a longer document. Its absolute addresses all change, even though the distance between its words stays the same. That suggests a different question. Instead of asking where each token is, ask how far apart 2 tokens are. Focus on the word bit. The dog is 2 steps to its left. The man is 2 steps to its right. Those signed offsets describe a local structure that survives if the whole sentence moves somewhere else. Relative position methods feed that distance and direction into attention. In one early approach, every pair of positions receives a learned edge representation based on the offset between them. Very large distances can be clipped so that everything beyond a chosen range shares the same faraway label. Other methods change the attention score directly. ALiBi, for instance, adds a distance-dependent penalty with different attention heads using different slopes. The implementation is different, but the family resemblance is clear. Position lives in the relationship between a query and a key, not only in an address glued to each token. Relative structure has an appealing symmetry. Shift both tokens by the same amount, and their offset does not change. The model can reuse a learned idea such as look 1 token back at many places in a sequence. Now, we can state the design goal more precisely. We want each query and key to know its absolute position, while their comparison reveals the relative distance between them. Rotary position embedding does exactly that with geometry. Take just two coordinates from a query vector and draw them as an arrow on a plane. At position 0, leave the arrow where it is. At position 1, rotate it by one angle step. At position 2, rotate it twice as far. Do the same thing to the key vector. The query at position 2 and the key at position 5 receive different absolute rotations. But attention does not inspect those arrows separately. It takes their dot product. When two rotated vectors are compared, the shared part of their rotation cancels, and the result depends on the difference between their angles. 5 minus 2. A relative offset of 3. That is the central trick behind rope. Absolute position determines how far each query and key rotates. Their attention score then carries a relative position relationship. The full vector does not spin around one giant clock. Rope divides the query and key into many pairs of coordinates. Each pair rotates at a different frequency. Some angles change quickly and distinguish nearby positions. Others change slowly and carry broader scale position patterns. The two-dimensional arrow is only one visible slice of that larger system. Rope is also multiplicative. Instead of adding a position vector to the residual stream representation, it rotates the projected queries and keys used for attention. Values are not part of this same rotary comparison in the standard formulation. Return to our sentence. Dog and man keep their content identities. Move them to new positions, and their query key phases change. That changes how their content is compared around biti. Word order has become geometry inside attention. But that geometry creates one more problem. What happens when the sequence becomes much longer than anything the model saw during training? A position formula may be able to calculate an angle for token 50,000. That does not mean the model learned how to use that angle. During training, the model sees only a bounded range of positions, offsets, and rotary phases. Its attention layers adapt to patterns inside that range. Continue the rotations far beyond it, and the equations still produce numbers, but the learned attention scores can behave badly. Experiments on rope-based ALiBi models made this failure vivid. Directly extending the position indices beyond the trained context caused perplexity to explode in the reported setup. The software could accept longer coordinates. The model could not use them reliably. Position interpolation takes a different route. Instead of extending the old ruler, it compresses a longer ruler back into the range the model already knows. A requested position in the larger window is scaled down before rope calculates its angle. With limited fine-tuning, the models in that study adapted to substantially longer contexts. That compression has a trade-off. Nearby positions become closer together in rotary phase, so the model must adapt to a denser map. Other extension methods alter frequencies or attention biases in different ways. This is why context length is not just a memory allocation setting. The position system helps define the geometry the model learned. A nominal window says how many tokens the implementation accepts. An effective window asks whether the model can still use relationships across that distance. No single position method guarantees that every token in a huge window will matter equally, or that retrieval will remain perfect from beginning to end. It does not discover order from the word inventory alone. A transformer injects a positional structure and learns to use it. Absolute embeddings attach an address to each slot. Relative methods describe the distance and direction between positions. Rope turns each query and key according to its absolute index, then lets their comparison expose a relative offset. Those mechanisms do not create meaning by themselves. They give attention the coordinates it needs to learn that dog before bit and dog after bit are different relationships. Put the two sentences back on screen. The dog bit the man. The man bit the dog. The content colors are the same. The positional geometry is not. That difference can flow through attention, through the transformer block, and into the model's next token predictions. One boundary is still missing. During generation, a token must not look ahead at words that have not been produced yet. Episode 8 adds that causal mask then follows the model from a context to a probability distribution and one chosen next token.